For number 8, when we're trying to review, what I want to do is a u sub, and I want to let u equal 1 minus x squared, and then the derivative of u is going to equal negative 2x dx. Now, I notice right away that my x dx will simplify with this dx and this x dx. So that's nice, but I have to bring this over to the other side. So I'm going to divide both sides by negative 2, and that's going to give me 1 over negative 2. So 1 over negative 1 over 2, and I'm going to be in the u world now because my x dx simplified, u du. And notice I left my limits of integration empty. What I'd like to do is continue in the u world. And what I mean by that is I'm going to change these limits of integration. This means when x equals 0, I'm going to integrate. However, I need to write in u what the value for u is. So when x equals 0, if I plug 0 into that, 1 minus 0 squared, u is going to equal 1. New limit of integration. When x equals 1, and I plug it in over here, when x equals 1, 1 minus 1 squared, u is going to equal 0. This was a little perplexing because now I have an upside down integral from 1 to 0. We usually do it the other way, and that's okay. We can rewrite it from 0 to 1, but when we do that, we must change the sign out front. So this is a legal move. And now I can just stay in the u world. The antiderivative of square root of u is going to give me 2/3 u to the 3/2. Don't forget the 1/2 is out front, so I have to bring that 1/2 over. Leibniz notation from 0 to 1. Not bad. Notice, the 2's will simplify, and this is just going to give me a 1/3 out front. So, 1/3, 1 to the 3/2, minus 1/3, 0 to the 3/2. That's going to give me 1/3 minus 0, or just 1/3 as my answer. For number 9, what I'd like to do is visualize this as an integral of 1 over cosine squared dx. Now, I'm not good at taking the antiderivative of 1 over cosine squared, but I know that to trig identity, this is going to give me secant squared x dx. Now, the antiderivative of that is just going to equal tan x. I'm going to continue with my limits of integration from pi over 6 to pi over 4. That's going to give me tan of pi over 4 minus tan of pi over 6. Tangent of pi over 4 is 1, minus the tangent of pi over 6 is root 3 over 3. And I can either read my answer like that or rewrite it as a common denominator, 3 over 3, which would give me 3 minus root 3 over 3. Or you could have just left it as 1 minus square root of 3 over 3. Either. For number 10, I'm just going to jump right into the antiderivative. That's going to give me 1 over 2, because I have to divide by the derivative of that, e to the 2x from 0 to ln of 3. So this is going to give me e to the 2 ln of 3 over 2 minus e to the 2 times 0 over 2. Now, when I have that 2 out front, that means I can bring it up and exponentiate it. So that's going to give me ln 3 squared, which is 9. So that's ln of 9. E to the ln of 9 is going to just give me 9 over 2 minus 2 times 0 is 0. E to the 0 is 1 minus 1/2. That's going to give me 8 over 2 or just 4. Number 11 is an alternating series. I get that from the negative 1 to the n minus 1. And the deal is, with an alternating series, I can ignore that, and I need to look at the limit. Not the limit of convergence, all right? Not the limit of the sigma notation, just the limit of 1 over n squared. Does that go to 0? So the limit as that goes to n goes to infinity is going to equal 1 over infinity squared, which lo and behold is going to equal 0. So the limit does equal 0. And that's beautiful. Now all I need to do is show that they get smaller. So that's going to be 1 over n squared. And when I plug in a 1, that's going to give me 1 over 1. When I plug in a 2, that's going to give me 1 over 4. When I plug in a 3, that's going to give me 1 over 9. And the second stipulation is that a sub 1 must be less than a sub 2, must be less than, greater than a sub 2, greater than a sub 3. That means they're getting smaller as you go to the right. Therefore, it does converge, and it's an alternating series. It converges, and it's an alternating series. This one I can see instantly that it's a harmonic, and all harmonic series diverge. So this one diverges, and it's harmonic. This is a geometric. His first term is 1, but his common ratio is greater than 1. So that means it's a geometric that diverges. Number 14, that's a power series. And it converges because p, the exponent, is greater than 1. So that's going to be a converging power series, or p series. Number 15. Again, another p series. But notice, p, my 3/4, is less than 1. So this is going to be a divergent p series. This is an e, and e equals 2.718, approximately. And that means e is bigger than 1. So this is going to converge, and it's a power series, or a p series. This one's a little tricky, it's a little sneaky. I'm going to rewrite this as 1 over n to the 1/2. I can see now that it's a p series, but the exponent is less than 1. So that means it is going to diverge. Let's take a look at this one. This is going to be 1 over n to the 5/2. Remember, what's in the bucket goes on the bottom. Another p series, but 5 over 2 is greater than 1. So that one's going to converge. This is an alternating series. But when we look at the terms of this alternating series, if we ignore this, it's going to get larger as n goes bigger, or it doesn't decrease. So if I ignore that, I'm just going to get 4, 4, 4, and it's not bigger. So that's a diverging alternating series. For number 20, as I inspected, I noticed instantly that the geometric series, whose first term when I plug in 0 is going to be 2, its common ratio is 1/3, and the formula is always going to be 1 minus that common ratio. So 1 minus 1/3 is actually 3/3 minus 1/3. That's going to give me 2 divided by 2/3. Or I can rewrite this as 2 times 3 over 2. So those simplify, and it's going to converge to just 3 for number 20. For number 21, again, I notice instantly that this is a geometric series. Its first term, however, is not 2. I have to plug the 3 in. So that's going to give me 2, because the first term starts at 3 in this case, times 1/3 to the 3rd power. That's going to give me 2 times 1 over 27. So my first term is going to be 2 over 27. Now I have to divide that by 1 minus the common ratio, which is 1/3. Not that big of a deal, just a lot of arithmetic. So this is going to be 1/3. 1 minus 1/3 is 3/3 minus 1/3. So that's going to give me 2 over 27 divided by 2/3. That's going to change 2. I'm going to multiply it by the reciprocal. Times 3 over 2. This is going to wind up simplifying a couple of times. 3 over 27 is 1 over 9. It converges to the sum of 1 over 9. It isn't readily noticeable what this is, so what I'd like to do is bring the 2 out front. And now I'm going to rewrite this because 3 to the n minus 1, I could also rewrite this as 2 parentheses 1/3 to the n minus 1. Now I notice when I let n equal 1, that's going to give me 0, so my first term is going to equal 2. I have a common ratio of 1/3, which is less than 1, so it's going to converge, minus 1 over 3. 1 is going to switch to 3 over 3. This is going to give me 2 divided by 2/3. We're going to multiply it by its reciprocal, 2 times 3 over 2. And this is going to converge to just plain old 3. Number 23. I can see instantly that it's a geometric series. Let me see what the first term is when I plug in 0. When I plug in 0, the first term is going to be 3. Then I notice the common ratio is less than 1. But it's not that it's negative, it's that the fraction is less than 1. And this is going to be 1 minus negative 1/2. That's going to change to positive. So this is going to give me 3 divided by 1.5, which equals 2. This series converges to 2. I notice for 24 that the first term is negative 7. And then I do negative 7/3 divided by negative 7 over 1. I'm going to multiply it by its reciprocal. So that's times 1 over negative 7. So my common ratio is 1/3. And then I'm just going to do 1 minus 1/3, and we'll see what the arithmetic leads us to. That's 3/3 minus 1/3. That's negative 7 divided by 2/3. Negative 7 times 3 over 2. This is going to converge to negative 21 over 2. Little typo, I wrote 24 down twice, so I'm just going to do this one as a little extra tidbit. I'm going to plug in the 1. That's going to give me 4 times 0.5 to the first power. That means my first term is not 4. It's very misleading sometimes. My first term is 4 times 0.5, which is 2. It's geometric, and its common ratio is less than 1, so it's going to be 1 minus 0.5. So this is going to give me 2 over 0.5, and that's going to give me a sum of 4. These are a little tricky. I notice first that the bottom's going up by 1, and it starts at 3. So if n equals 1, 1 plus some number equals 3, so it's going to be n plus 2. And if I put my sigma out front, from n equals 1, so that first number is going to be 1 plus 2, that's 3. Then I throw in a 2. 2 plus 2 is 4. So it's creeping along. I'm feeling good about that. Now I notice this goes up by 2. So this is 2, 4, 6, 8. That's going to give me 2 times n. Let me throw in the 1. Throw in the 1, that's 2. Throw in the 2, that's 4. Throw in the 3, that's 6. But it doesn't go to infinity. I have to figure out where it starts. So it starts at 3, 4, 5, 6, 7, 8, 9. So that gives me 5 terms. 5 terms. Let me see here. So it's going to be 1. It's got to go to 7 to get me that up there. I messed up my count. Let's see. When I throw in 7 for my last term, 2 times 7 is 14. When I throw in 7 for my bottom term, that's going to give me 7 plus 2 equals 9. Now the top is not that bad. The top for this one goes up by 1, 2, 3, 4. So if I start at 1, I can just put n there. Notice it goes up to 5. So that's good enough. Now the bottom is what's tricky. I'm thinking factorial because I see the 120 and I see the 24. So I know that 1 factorial equals 1. 2 factorial equals 2. So that lines me up. 3 factorial, that's going to equal 6. So I want to see where I begin. So I can't start at 2 factorial or n factorial. I think I have to start at n plus 1 factorial. N plus 1 factorial. And that will generate the sequence. Let me throw in the 5. That will give me 5 plus 1, which is 6 factorial. 6 factorial is equal to 6 times 5 times 4 times 3 times 2 times 1. So this is 6. This is 6. That's 36 times 20. Now I'm shooting for that 720 on the bottom. Give me a 0. That's going to give me 72. Yep, it works. So number 27 is going to be sigma from n equals 1 to 5 fraction n over n plus 1 factorial. For 27, I notice it alternating from negative to positive, negative to positive. So that right away is going to clue me in that this is an alternating series. And all alternating series either start with a negative 1 to the n or n plus 1. I'm going to go for n. You could write these a couple of different ways. And I'm going to put a 1 here. That means this is going to give me negative 1 for the first term. Now I believe there's going to be a fraction. And it's going to be a 3 to the n. 3 to the first is 3. 3 to the second is 9. 3 to the third is 27. 3 to the fourth is 81. I have to figure out what the bottom is, and it's tricky because I don't have any fractions underneath of there. But 0 factorial is 1. 1 factorial is 1. 2 factorial is 2. So now I think I have to screw around with my notation because I'm going to need a 0 factorial. In order to get 0 factorial on the bottom, I need a 0 here. So it's going to be n minus 1 factorial. Let's see what happens when I throw the 1 in. I get 1 minus 1, which is 0 factorial, which is 1. 3 to the 1, and the negative up front. That works. Then I'm going to throw a 2 in. That's going to give me 1 factorial, which is 1. And a 2 would give me a positive 1 there because negative 1 squared is positive, and a 9. And that's how it's going to work for number 27. And you might have noticed that I was off one number, so I went ahead and corrected this. It was 24b, 25, 26, 27 I just did. This is going to go on until infinity, I believe. So this is going to give me sigma n equals 1 up until infinity because of the dots. Alternating 3 to the n all over n minus 1 factorial. For number 28, notice how I already set it up. I notice it's going from negative to positive, negative to positive. So I get my alternating negative 1 to the n. This kind of locks me in that I have to start at 1 because that's going to give me a negative 1 for my first term. The top is going to be 6 to the n because 6 to the first is 6. 6 to the second is 36. 6 cubed is 216. And I hope 6 to the fourth is 1296. I believe it is. And notice again, I have over 1, over 1, over 2, over 6. These are factorials. 0 factorial equals 1. 1 factorial equals 1. And then 2 factorial equals 2. 3 factorial equals 6. And these are nice to know. Just so you can see that that's going to be a factorial on the bottom. Now I need to start with 0 factorial. And once again, that's going to give me the n minus 1 factorial. And when I plug in the 1, it gives me a 0. When I plug in the 2, that gives me a 1. When I plug in the 3, that gives me a 2. So on and so forth. So this in sigma notation for number 28. And it goes on forever, so it's going to go up to infinity. Sigma notation from n equals 1 to infinity. Alternating negative 1 to the n, fraction bar, 6 to the n over n minus 1 factorial.